Audio check. 1, 2, 1, 2. We're good. I don't want to do the same mistake ever again. Okay, welcome back, guys, and welcome to Chapter 3, all about orbital perturbations or orbital disturbances that will be naturally influencing the attitude of the spacecraft motion as the spacecraft orbits around the Earth, because this is the environment into which any spacecraft happens to be traveling through, okay? The space environment is creating a lot of perturbing torques due to the solar radiation pressure effect, which is the interaction of the sun's photons hitting the panels of the spacecraft. Spacecraft in low Earth orbits are experiencing a lot of drag due to the fact that they are traveling through an atmosphere with some atmospheric density, and thereby that will reduce the orbital energy, as we said in orbital mechanics, but that will also torque the spacecraft around its center of mass. Also, we have gravity gradient due to the fact that the spacecraft may have an orientation with respect to the gravitational attraction of the Earth that will tend to naturally align the spacecraft. Okay, so this is known as gravity gradient, which is happening because gravity is pulling the spacecraft towards the primary body. And also we have magnetic torque that are torquing the spacecraft around due to the interaction of the electronics components within the spacecraft itself, which are creating kind of a dipole or a magnet, if you will, within the spacecraft. And that magnet is interacting with the Earth's magnetic field and thereby creating a torque that will always try to align the dipole with or along the magnetic field of the Earth. So those effects are there no matter what you do, okay? And although in the previous chapter we had considered that the motion was torque-free for simplistic analysis, and that was just to get analytical expressions for the angular velocity components in a body fixed as function of time, so that we could try to wrap our head around conceptualizing the motion in 3D space. But in practice, perturbations will always be there. So the torque-free assumption does not hold for practical purposes, especially if you look at simulating, say, or analyzing the rotational motion of the spacecraft over a long time period, okay? So the torque-free assumption, as I mentioned previously, was kind of valid for a short time scale. Whenever you look at analyzing the motion, rotational motion over one, over two, over multiple orbits, then we do need to take into account orbital perturbations because they will influence the rotational motion quite a bit. Okay, that being said, we will not be able to obtain analytical expressions to analyze the rotational motion of our spacecraft. So if you want to see, say, the time evolution of your attitude representation you had selected under perturbing torques affecting the spacecraft, then you need to numerically integrate the resulting equations of motion, and you do that through MATLAB Simulink. All right, let's dive in. Chapter 3, all about attitude perturbations. Or disturbance torques that are created by the space environment that will be applied to the spacecraft. More specifically, if you go back to Euler's equations of motion, J times omega b dot plus omega b skew symmetric J omega b equal to the net torque applied about the center of mass of the spacecraft, as we had seen in Chapter 1. Well, the goal of this chapter is to figure out exactly what will be the perturbing torques that could be modeled on the right-hand side of that equation. Specifically, we're going to look at the magnetic torque, okay, in a body fixed reference frame created by the interaction of the spacecraft and the magnetic field of the Earth. We're going to look at the drag torque or the aerodynamic torque created by the fact that the spacecraft travels through a non-zero density atmosphere. We're going to look at gravity gradient torque, which will always align the spacecraft along the specific axis due to the fact that the bottom part of the spacecraft will be more attracted towards the ground or towards the Earth as the upper part, because the further you get from M1, the less the gravitational pull will be. So that difference in gravitational forces at both tips of the spacecraft will tend to torque the spacecraft, okay? And we're also going to add the solar radiation pressure torque due to the sun's photons interacting with the spacecraft itself. Okay, so how can we model each of those individual perturbing torques is going to be the focus of this chapter. And then we could simulate that in MATLAB Simulink to get an expression for omega b dot, integrate that, get omega b, feed omega b back into this equations of motion, repeat the process, and ultimately feed omega b to kinematics, and then see the time evolution of the orientation of our spacecraft due to some initial conditions on omega b and onto the attitude itself under the influence of perturbing torques affecting the overall motion. All right, so the first one I'm going to have a look at is the magnetic torque in 2.1. So magnetic torque exists due to the fact that a spacecraft has a bunch of electronic components inside of it, okay? We have power regulator, power distribution unit, computer, sensors, actuators that might be controlled by solenoid valves, and all those things are a bunch of electronics all together wired in some fashion. The solar panels have a bunch of wires coming through the computer and whatnot. So there are a lot of wires inside a spacecraft, and thereby a lot of current is flowing through. Now, the currents are flowing in some random direction, but we could always model all those currents as a single current loop. And as you know, a current loop creates a magnetic field. All this to say that the spacecraft is generating its own magnetic field, okay, because of all the electronic components. Now that magnetic field of spacecraft will be interacting with the magnetic field of the Earth, which is always there, okay? And by the way, the magnetic field of the Earth is quite complex. It is an asymmetric field. It's not perfectly symmetrical around the Earth, and it's not directly aligned with the spin axis of the Earth. So to model the magnetic field of the Earth is quite an extensive process, and we're going to go through the process together in this chapter. But we'll see ways that we can always model the magnetic field of the Earth in simpler forms. One of which is just by considering a dipole model and a tilted dipole model from the North Pole of the Earth. And then based on that, we're going to see the interaction of the spacecraft with that tilted dipole, okay? So, first things first, the magnetic torque in terms of vector acting on a spacecraft can be calculated as the interaction of the magnetic dipole vector of the spacecraft created by the electronic components running wire or running current through the multiple wires of the spacecraft, cross product with the Earth's magnetic field vector. Okay. Now the question is in 2.1.1, how can we model this Earth magnetic field vector? Or specifically, we're going to have a look at different magnetic field models, ranging from the most generic / most complex one down to the most simplistic one that we're going to use for all practical applications within the context of this course, okay? So let's do that. So the first model, being the most accurate one, is known as the spherical harmonic model, like that. Now, I'm not sure if you remember, but from orbital mechanics, we had looked at the J2 perturbation, okay, due to the oblateness of the Earth creating an accelerating force, perturbing acceleration on the spacecraft, perturbing torque or thrust, sorry. I don't want to mix things up too much here. But the J2 was derived by taking the potential function as a double summation in terms of spherical harmonics involving Legendre polynomial and Gauss coefficients and things like that. And then we had looked at the first degree and first order of that double summation equation to end up with the J2 effect at the end of the day. And then taking the gradient of this potential field, we had then obtained the perturbing acceleration due to J2. Well, here is going to be the exact same thing, but in terms not of potential field, but in terms of magnetic field. And you will see some similarities between potential field in terms of spherical harmonics and magnetic field. First one is that the magnetic field vector itself is obtained as minus gradient of the magnetic potential function denoted by V here, okay? This is analogous to our perturbing let me stop drawing relationships between this and orbital mechanics. We don't need to remember that, okay? And I don't want to do a silly mistake here. But that was something similar to derive the J2 perturbations. Let's leave it as that, okay? So knowing this, next thing we need to do is look at how can we get the magnetic potential function V. And the answer is that we're going to obtain that through a spherical harmonic relationship, which tells us that we're going to need to take the mean equatorial radius of the Earth times the summation from degree equal 1 all the way to K. And then mean equatorial radius of the Earth, that's your 6,378 kilometers over the distance between the planet and the spacecraft, instantaneous position or distance, to the power degree, which is n plus 1. And then another summation from order equals 0 all the way to the degree of Legendre polynomial functions. That will be function of theta. Theta will be defined as the co-latitude of the current spacecraft position along its orbit. This will multiply G and M cos of the order times the longitude, lambda, plus another coefficient of degree n order m times sine of order times longitude lambda. Okay? So, just to sum things up here, this here is a constant. That's 6,378 kilometers, the mean equatorial radius of the Earth. This r is the norm of your position vector on orbit. This is a Legendre polynomial. Of degree n and order m. And its Legendre polynomials are a function of whatever variable of interest. Here the variable of interest is theta, and theta here is not related to the earlier angles, okay, or not related to what we saw in chapter 2, but this time it's going to be related to the co-latitude, which is mathematically obtained as being pi over 2 minus the actual latitude, denoted by delta, okay? And I'll draw that on the board at one point to better illustrate this. Lambda here is the spacecraft longitude at that given instant. M is your order of the Legendre polynomial. And those two things here are Gauss or Gaussian coefficients. Gaussian coefficients of degree n and order m. Nice. Well, nice and not too nice, because it means that in order to ultimately obtain the magnetic torque affecting the spacecraft, we need to simulate the orbital motion, because we need to know r, the position between m1 and the spacecraft instantaneously, as well as the latitude and longitude. Okay? And the way that co-latitude is related to latitude is, if you look at the ECI reference frame, IZ pointing up, IY to my right, and IX out of the board. This is, of course, centered at the Earth, at the equator. Latitude, based on the current spacecraft position along its orbit, is this angle from the equator being at 0 all the way up to 90-degree latitude, right? That's your delta, such that co-latitude is simply pi over 2 minus latitude. This is your theta right there. So measured positive from IZ instead of being measured from the equatorial plane. Okay. But it turns out that it becomes quite a bit more complex, because the problem is that those polynomials, p of degree n and order m as function of the co-latitude, need to be what's known as Schmidt, S-C-H-M-I-D-T. Those are Schmidt normalized. Those are obtained from Legendre polynomials that are Gauss normalized, referred to as P and M function of co-latitude. Okay, so those are Gauss normalized Legendre polynomials. As here on this side, and that's what we need to obtain the magnetic potential function V, are Schmidt's normalized Legendre polynomials. Okay? And what is the relationship between both? Well, we need to use a normalizing function known as the Schmidt's S-C-H Schmidt, German. I should know because Ulrich is from Germany, but I have a hard time pronouncing that. Schmidt. Quasi-Normalization Factor. Okay. Now this is making things a bit more complex. So the Gauss-Normalization polynomial can be easily obtained as follows. So P of degree 0, order 0, nonlinear function of co-latitude, easy peasy, that's always equal to 1. Now P of any n, comma n, of colatitude will be equal to sine of our colatitude angle times P n minus 1 and n minus 1. So this is a recursive way to obtain the Gauss-Normalized Legendre polynomials so that ultimately we can calculate the Schmidt's normalized Legendre polynomial and plug that into the magnetic potential function. So this is quite a time-consuming and potentially complex process. And whenever we're going to look at nm instead of nn, this one is going to be calculated as cos of our colatitude times the Gauss-Normalized Legendre polynomial of degree n minus 1 and order m minus k degree n order m of Legendre Gauss-Normalized Legendre polynomial of degree n minus 2 order m. Are you kidding me? No, I'm not. That's the way it works, okay? But don't worry, there's hope. At the end of the day, we're going to see how we're going to use MATLAB to get all of this for ourselves. But the process here is important because I want you not to use MATLAB as a black box, but to understand what's going on backdoor. So make sure you understand where things are coming from and how to do the mapping between Gauss-Legendre polynomials and Schmidt's normalized Legendre polynomials, because that could end up in an exam, okay? Where here we need to define the k factor here, where k of degree n order m is going to be equal to one of two things. 0 whenever the degree n will be exactly equal to 1, or n minus 1 square minus m square, all this over 2 times n minus 1, 2 times n minus 3, and that is whenever the degree is larger than 1. Poof. Okay. Now that's good. We kind of know how to calculate this, but what about the quasi-normalization factors? Well, I'm going to give you the answer to that term as well. So whenever S, you're talking about order and degree equal to 0, this normalization factor will be exactly equal to 1. Yes, we like it. That's good news. Whenever we're going to talk about any degree and an order 0, we're going to get a recursive formula again, n minus 1 of order 0 times 2n minus 1 over n. Okay? And whenever you're talking about degree n and order different than 0, this normalization factor will be degree n and the previous order, m minus 1, times the square root of n minus m plus 1 times delta m1. Okay, plus 1, and I'll define that in a second. All this over n plus m. Not so fun, isn't it? Doesn't look nice at all. But that's the way spherical harmonics in terms of some random degree and order work. There's no shortcut around that, unfortunately. Okay, but we're going to see ultimately how to simplify it and how to limit the degree and orders and how to make it something more practical that we as engineers can end up using, because this is straight from mathematical textbooks, okay? This is not from engineering textbooks, but this is where things are coming from. And therefore, I feel that this is important to understand. Okay? This guy here is known as a Chronicler, like that, delta. Okay? Which is given by one of two things. Ing is going to be equal either to 0 or 1. 1 whenever I is equal to j, and 0 otherwise. So in that sense, whenever m is equal to 1, you're going to get your I equal to j, and that will turn up to be 1. Whenever m is going to be different than 1, then this will be 0 altogether. Okay? Great. So now, given this, obtained by the multiplication of this quasi-normalization factor, the Gauss-Normalization polynomial, then you can evaluate the magnetic potential field V. Okay? Well, wait, didn't we needed the J and H coefficients in that expression? Well, yes, obviously. Turns out they are they need to be Schmidt normalized as well. Okay, so we have J. Well, no. Let's talk about J and H in a second, because with that we have everything we need to calculate V. Okay? And if you were to take the gradient operator, then you get BR, B theta, and B lambda. And the reason why I'm not specifying how to get G and H in V is because I'm giving you directly the equations for the gradient of V. Okay? I'm going to give you the relationships for these three things, which we'll see will no longer be function of G and H as they were in V. They're going to be function of a different versions of G and H, which I will then define for you. Okay? So BR is the x component of the magnetic field vector obtained by the gradient of the magnetic potential function in a reference frame that has its x unit vector radially out, its y unit vector, how is it called? Just south positive, and lambda here being east positive. So this is the co-elevation component. This is the azimuthal component of the magnetic field, and this is the radial component. So in a way, this is the magnetic field expressed in a spherical type of reference frame. Okay, let's leave it as that. So this is going to be equal to the summation of degree n equal 1 up to some random degree k of mean equatorial radius of the Earth, or R, to the power degree n plus 2 times n plus 1 times m equals 0 to n of p and m of co-elevation, and this is your Legendre polynomial, which we looked at just previously, times, and now instead of having g and m like that we had in the magnetic potential function V, now these turn up to be n m like that, or Schmidt normalized potential coefficients. All right. I see where you're going with that. You're going to need to convert from Gauss-Normalized to Schmidt-Normalized again. The answer is yes. Okay. H and M of sine M latitude like that. This is all for BR. B theta minus summation of n equal 1 to k, mean equatorial radius of the Earth over r. All this to the m plus 2. Then summation of order of degree from 0 to degree equal to order n of partial derivative of Legendre polynomial to the nonlinear function of co-elevation with respect to the co-elevation itself times this coefficient g of degree n and order m, which has been Schmidt normalized, of cos m lambda longitude plus h and m sine m times longitude, like that. And lastly, the z component of the magnetic field seen in that spherical reference frame is going to be minus 1 sine theta summation n equal 1 to k of r Earth over r to the power m plus 2 and times the summation m ranging from 0 to n of the Schmidt normalized Legendre polynomial nonlinear function of the co-latitude angle theta times m. All this times minus g and the Schmidt normalized coefficient here, and then same thing, m longitude plus h and m cos m times longitude. Whew. Okay. Now we're getting down the rabbit hole very quickly here. This is mathy as hell, right? But again, what we know and what don't we know, and those x, y, z components of the magnetic field. So we're past the gradient operator. That I did that for you and I gave you the answers here, okay? But yeah, to evaluate the field in terms of x, y, z in that reference frame, which is not very important because that's kind of just an intermediate reference frame, we need to know this. This is your 6,378 kilometers. This is the norm of the position vector at the current time for the spacecraft with respect to the primary attracting body M1, obtained by solving the two-body equation from orbital mechanics. It's up to us to decide how accurate we want to model the magnetic field of the Earth by selecting a degree and order of whatever. If we want to go very accurate, we could select those two coefficients, or n and m, to be equal to 100 and spend a month to derive everything by hand, or use a computer and do it very quick. Or if we are restricted to hand calculations, we'll see what we're going to end up with should we limit those order and degree to be something more manageable, okay? So n and m are up to you. We have seen how to calculate the Schmidt normalized Legendre polynomials as function of the quasi-normalization factor. These were the S terms, and I gave you the answer for the S terms based on the Gauss-Normalized Legendre polynomials. So based on, was it n, bottom, like that, okay? So based on that, we calculate the quasi-normalization factor S to get the Schmidt normalized Legendre polynomials and plug them back here. Those coefficients G and H will also be obtained from the Gauss-Normalized factor or coefficient G and H, multiplied by the quasi-normalization factors S again to obtain the Schmidt normalized coefficients G and H from G and M and from H and M. M is the order that we had selected as a designer based on the accuracy we wanted out of this spherical harmonic model. Lambda is the current spacecraft longitude, obtained by solving the two-body equations by looking at the x, y, z components in ECI, turning them into the Earth-centered, Earth-fixed inertial reference frame. That was our ECF reference frame. And how to go from x, y, z in ECF to latitude, longitude. Well, we have all the equations to that in orbital mechanics. So that is known or can be easily calculated. So essentially, although this looks terrible as it is, we have all we need to calculate it. But these things here, right? Because I told you that to get what we needed in the expressions, we needed to turn these to that via the quasi-normalization factors S. But where do we begin with? Or where do we begin at? Or how do we get those things in the first place such that we could transform those Gauss-normalized things to the Schmidt normalized things that we need in those expressions? Turns out those are given to you, okay? Given to you by an organization whose job is to figure these things out for us by combining ground-based data, by combining satellite observations, and all other bunch of stuff, aircraft-mounted scientific equipments measuring the magnetic field of the Earth, and so on and so on. All these data are being collected together and provided by an organization called IGRF. And they publish those data on a website. Sorry, this is not the organization. This is the name of the model, which is related to the spherical harmonic model I gave you in the first place, to the potential magnetic function, V. So the International Geomagnetic Reference Field Model is the spherical harmonic model for an arbitrary degree and arbitrary order I gave you in the first place. So the coefficients that you use in this model are the Gauss-normalized coefficients that are obtained from the IAGA organization. Organization with an S, probably. Organization, yeah, that was better. Or whose objective is to collect all those data obtained from satellites, from ground station, from aircraft, UAV, you name it, and they combine that and provide a list with the Gauss-Normalization polynomial, the G coefficient in terms of Gauss-normalized, and the H coefficient as well for an arbitrary degree and order. All this information can be found on a website that I gave you in the lecture notes as a footnote. And the website is a page of the NOAA organization in the States, which is the organization in charge of collecting all the data from Earth observation weather satellites. The GOES that are the geostationary satellites. This is GOES, and the NOAA low Earth orbit satellites that are monitoring the Earth. Okay? Turns out that because this is quite an extensive job, they only update the values on the website every 5 years. Okay? So For example, they had provided values in 2010, in 2015, 2020. We'll provide another updated list of coefficients in 2025. But along the numerical values for those things, they also provide the rate of change per year. So if you happen to be in 2023, all you have available, the latest sets are the 2020. So you take the 2020 data and you extrapolate them using the annual rate of change over 3 years, okay? And you calculate that for yourself. And then you get those, convert them into Schmidt normalized, and use them for your own purpose, and that is to get the potential field, magnetic field of the Earth. Okay. Good. So how to turn then those coefficients into the Schmidt normalized? Exactly the same as we did for the Legendre polynomials. It's going to be G and M, Schmidt normalized, equal to the normalization factor, same as before, times the Gauss normalized that you get from this organization, and same for H, and M equal to S and M and H and M. Gauss normalized, Schmidt normalization factors, and Schmidt normalized at the end of the day that you can use into now BR, B theta, BZ. So you don't need to worry about the magnetic potential function V anymore, because I took the gradient for you guys and just plug these back into BR, B theta, BZ. But if you remember, for the B theta equation, there was the partial derivative of the Legendre polynomial. Oh boy, we are not done. No, we're not done. Okay? So I have to tell you how to calculate the partial derivative of the Legendre polynomial depending on the degree and order with respect to the co-elevation angle theta. Whenever degree is equal to order equal to 0, this partial derivative will simply be equal to 0. That's good news. It's a good start. We like zeros. But whenever the degree is equal to the orders and n with respect to the co-elevation angle, we're going to get sine of co-elevation, partial derivative of degree n minus 1, order n minus 1. So again, this is a recursive formula that we need to apply. Partial derivative with respect to theta plus cos theta of Legendre polynomial Schmidt normalized of degree n minus 1 and order n minus 1 as well. Okay? And whenever the degree is different than the order and both different than zeros, because whenever they're both equal to 0, we know that this partial derivative term ends up to be equal to 0, will then be equal to cos of the co-latitude, partial derivative, oh no, so this is a recursive expression again. Yes, it is. This with respect to co-elevation minus sine of co-elevation and recursive Legendre polynomial of degree n minus 1, order m minus k. Remember the k terms we had defined previously, now it comes back. And then partial derivative, oh boy, of degree n minus 2, order m with respect to co-elevation. Not straightforward, isn't it? But doing so, plugging this back into BR, B theta, BZ, does not really give us what we need as an engineer to simulate the rotational motion of the spacecraft under the influence of the gravitational perturbing torque. Correct? Because what we need is the components of the magnetic field of the Earth in the body fixed reference frame. So it'll make more sense, such that we obtain the torque in the body fixed reference frame and use that practically in Euler's equation of motion. But to do that, we first need to convert BR, B theta, BZ, BR, B theta, BZ, to ECI using CI, and that reference frame, the spherical reference frame, was referred to as Dipole reference frame, to get Bx, By, Bz, or components of B in ECI reference frame. Okay? Now, if you do so, you will end up, I'm going to switch color because my black marker is dying on me. I'm going to switch to blue. You're going to get, if you were to calculate that and multiply everything, and the process here is not that important, the result here is more important. You're going to get Bx, By, Bz, or the components of the Earth's magnetic field in ECI, modeled through the spherical harmonic formulation, equal to BR, for which we had the expression before, cos latitude plus B theta sine latitude. All this times cos longitude plus theta GMT, which is the angle between Ix unit vector and the x unit vector of ECEF, right, which is the reference frame attached to the Earth and rotates with the Earth. Whenever the x unit vector of ECF is aligned with Ix of ECI, this angle is 0, so it turns from 0 to 2 pi in a day. Okay, so 2 pi over 1 day would be theta GMT dot. But theta GMT is just the angle. So this times that minus the Z component of the magnetic field in the spherical reference frame, the intermediate reference frame that we never really defined, but that's not important here. Cos of longitude plus theta GMT. This is Bx. By is going to be equal to Br cos latitude plus B theta sine latitude. All this multiplying sine longitude plus theta GMT minus B lambda of cos longitude plus theta GMT, like that. And finally for BZ, we're going to get BR times cos latitude plus B theta cos latitude, simply. Okay? So this is just coming from the expansion of this particular rotation matrix in terms of a 3 by 3. I'm getting Bx as a function of Br, B theta, Bz, which is essentially what we did here. And same for By and same for Bz. That gives us the magnetic field vector expressed in terms of its x, y, z components in ECI, Earth-centered inertial, but that's not really what we want, right? Because I said that we wanted to have the field in the body fixed frame such that we could then take the magnetic dipole of the spacecraft M, expressed in terms of the body fixed reference frame, and then be able to take the cross product, or because now we're talking about components, take the skew symmetric and obtain the perturbing torque in the body fixed reference frame, okay? But we're going to leave that to a little bit later today, because the objective of the different models I'm going to present you will be first to obtain the field in ECI, and then it's going to be up to you to select the model that you want to use to model the magnetic field of the Earth in ECI. And then you take either this set of Bx, By, Bz, or the simplest one we're going to derive today, and then we're going to go from this to body fix, okay? Because I don't want to repeat the conversion from ECI to body fix whenever I present a new magnetic field model. We're going to save that for later once we have selected the appropriate model for the magnetic field based on the accuracy you are looking for. So that was the spherical harmonic model, the most accurate we can think of. Okay? The second one is known as the world magnetic model. Okay? Which models the magnetic potential field V by taking only degree up to 12. So instead of having an infinite summation, which works for degree in order up to n and m respectively, and potentially consider n equal 20 and m equal 25 or whatever, that one limits itself to degree up to 12. Because it was shown that limiting the degree to 12 is a very good approximation of the actual magnetic field of the Earth. Going above 12 doesn't give us much benefit, such that if you go back to the double summation equation for the spherical harmonic, you just limit degree to be 12 instead of being some random number, and then you write everything like this. Okay, nothing new here. Sine order times longitude, like that. And the beauty of that is that MATLAB has a built-in function called the world magnetic model that you have to type as WRLD for world, mag, the magnetic, and M for model, that based on the current spacecraft altitude above the surface of the Earth, so you need to take the magnitude of your position vector minus the radius of the Earth, which is your 6,378 kilometers. All right, so that is the first parameter you need to give MATLAB to evaluate this world magnetic model function. Then you need to provide the latitude, the longitude of the spacecraft, and then finally the year in terms of, I don't know off the top of my head, but if you type help, this function MATLAB will tell you exactly how to provide the year in terms of its decimal year, by the way. So that means that you are specifying the day, the month, the year, and potentially the time of the day as well, to be super accurate. I'm not sure, but again, just type help of world magnetic model in MATLAB, and that will specify you exactly how to give this parameter to this function. And as the output, you get a couple of things. You get X, Y, Z, H, declination, dipole, and H. Out of all those great things that this function provides you with, what matters here is X, Y, Z, because X, Y, Z are the X, Y, Z components of the field given by the NAD reference frame, which is north, east, down reference frame. NAD, right? And ED. So if you have, say, the Earth, that reference frame would have its X unit vector pointing towards the north. Its Y unit vector pointing towards east. And so that would be in the direction of PN, if you will, direction of E. And down would be cross product of X and Y of NAD, so coming towards the Earth, so or down, okay, looking down at the Earth. Like that. All right? So, it's easy, right? Just figure out altitude, longitude, latitude, decimal year at which you want to evaluate the field of the Earth. Plug that into MATLAB, and MATLAB will calculate for you the X, Y, Z components of the field. But in this specific reference frame, which doesn't really interest us, what we'd rather have is ECI directly, but instead we're going to go through BR, B theta, and B lambda to begin with, as we did for the spherical harmonic model. And the conversion between that reference frame and NAD is such that when you expand everything, you're going to get minus Bn sine of the geodetic latitude. No, sorry. Sine of epsilon. Now I'll show you how to calculate epsilon. Come on. Sine of epsilon. Sine of epsilon minus the Z component that MATLAB is giving you, which is along the down direction of NAD reference frame, cos of epsilon. Beta is going to be minus the X component provided by MATLAB, cos epsilon, plus the Z component, sine of epsilon, and finally the Z component is going to be the Y component provided by MATLAB here, so BE. Okay, so BN, BE, and BD right from the MATLAB function. That's great news. But you need to figure out epsilon so that you can get BR, B theta, and B lambda, and use those and turn them into Bx, By, Bz, as I showed you in the previous section for the spherical harmonic model. Okay. So epsilon is going to be equal to the geodetic latitude phi minus delta, where delta here denotes this parameter calculated by MATLAB, which happens to be the declination angle. Okay, so this is the geodetic latitude, which corresponds to, if you look at a quadrant of the Earth, this is IZ, this is IY, and IX to be out of the board like that. So the spacecraft happens to be here, orbiting around the Earth along its orbit. You have two types of latitude that you can look at. The first one is the geodetic latitude, geocentric latitude, which is calculated from here in the center of the Earth, hence the name geocentric latitude. Geodetic latitude corresponds to the latitude calculated from a fictitious position vector, which happens to be perpendicular to the Earth's surface. And that is the geodetic latitude angle that you need to calculate epsilon into those equations, okay? And the reason why geocentric latitude is different than geodetic is because the Earth isn't a perfect sphere. Otherwise, those two angles would be exactly the same, right? By virtue of the non-sphericity of the Earth, this angle here is not 90 degrees, but it's something else, such that the angle here, or the geocentric latitude, is not the same as geodetic latitude. Here, you're looking at geodetic for this calculation. Okay? And based on this, you can go from this to bx, by, bz, as I showed you in the previous, with the previous model, and ultimately we'll see how to turn those three components into the body fixed reference frame. Okay, so that's very great. MATLAB does all the work for you, basically. The last one is the dipole model. So instead of considering a very complex asymmetrical magnetic field of the Earth, we're only considering that the magnetic field of the Earth is modeled as a simple dipole, or a magnet, if you will. Okay? A magnet which is inclined with respect to the north pole of the Earth, hence the name tilted dipole model, or just dipole model. Okay? So the dipole model is what people use when they want to do quick calculations, or when they don't care about using a very accurate magnetic field of the Earth for their practical application. Which means that for this we're going to limit n, so the degree to be exactly equal to 1, and we're going to let the order vary between 0 and 1. Okay? So degree equal to 1 and order 0 to 1. And turns out that this very simple tilted dipole model is accurate to about 90% of the actual very complex magnetic field of the Earth. So that is a good approximation. Okay? So doing so would simplify our potential magnetic function V to be the cube of the mean equatorial radius of the Earth over the distance squared between M1 and the spacecraft times P01, function of co-latitude angle, G10, plus P11 of co-latitude, and multiplies G11 cos longitude plus H11 sine longitude. Wow, isn't that great? This is a lot more neat and compact than using the double summation of everything with partial derivatives involved in the process and all that. This is a lot simpler to play with. Okay? And turns out that explicit formulas for the Schmidt normalized Legendre functions or polynomials are going to be for P01, the nonlinear function of this variable, is simply cos of the angle, and your P11 nonlinear function of the co-latitude will simply be sine of your co-latitude angle, such that with that in mind, okay, you could substitute your Legendre polynomials with what they happen to be, specifically for these circumstances. for this circumstance. And here you get G1 naught cos of this angle, and that one turns to be sine of co-latitude simply. Okay? With that, and keep in mind that those are coming from the IGRF or the website directly. But the good news is that if you were to evaluate the gradient of this potential magnetic function, you would get for BR, B theta, and BZ expressions that look like 2 mean equatorial radius of the Earth over distance, all this cube, times this that you fetch from the website, cos co-latitude plus G11 obtained from the website data, this plus H11 sine of longitude, now this sine of co-latitude angle. For B theta, you would get a similar relationship, this cube times G1 naught sine of the angle minus G11 cos of longitude plus H11 sine of longitude, all this cos of co-latitude angle. And lastly, oh, that's not BZ, that's B lambda, because we're still within that spherical kind of reference frame. Going to be our Earth over distance cube times G11 sine of longitude minus H11 cos of longitude. All right? So now we looked at 3 different ways to obtain the, and then obviously you turn that into Bx, By, Bz, or the XYZ components of the magnetic field of the Earth seen in the Earth-centered inertial reference frame. Okay, and now we've seen 3 different ways to obtain Bx, By, Bz. Now the only question that remains is how can we use that practically to calculate the magnetic torque affecting the spacecraft in the body fixed reference frame. Okay? And you'll see that it's not that difficult to do because you'll just have to go back to the expression we had for the magnetic torque vector in vector form, which was the magnetic dipole moment of the spacecraft itself due to its current loops, cross product with the magnetic field in terms of vector. Well, in Euler's equation, in order to be able to use that, we need to turn that into components in a body fixed reference frame, which is the reference frame used inherently in Euler's equation of motion. And then I'm going to write TMB equal to the magnet, if you will, created by the internal electronic components of the spacecraft. It's Q symmetric to the components of the magnetic field in the body fixed reference frame, denoted by B subscript B. Now, so far we had obtained analytical expressions to calculate the field of the Earth, but in ECI, right? This is where our Bx, By, Bz are referring to. So all we need here is to use the attitude matrix or the rotation matrix from ECI to the body fixed reference frame. And we know how to get that from chapter 1, right? in order to get the torque applied onto the spacecraft expressed in the body fixed reference frame, and then use that in Euler's equation, which is our J, omega b dot plus omega b q times J times omega b equal to the net external torque applied to the spacecraft. Well, if you only want to see the effect of magnetic torque on the spacecraft motion, you just have to plug this back into Euler's equation like that. By the way, this term here is known as the gyroscopic effect and will cause the spacecraft angular velocity vector to change as a function of time, even though there's no torque applied to it, as we saw in the previous chapter. Remember that our angular velocity vector was spinning in the body fixed reference frame, thereby having this to be equal to non-zero, although there was no torque applied, okay? And this is due to the gyroscopic effect or term in that Euler's equation. Fantastic. Great. So 3 ways to model the Earth's magnetic field. And then based on that, just do simple skew-symmetric multiplication here to get the torque due to the magnetic field of the Earth into the body fixed reference frame. The last thing I didn't talk about is this. So this MB as a column matrix will be provided to you by the electronic engineers working under your supervision. Okay, it's not up to you to determine that because this is a highly complex scenario where everything has to be modeled in terms of electronic components and capacitor and inductance and current inside the spacecraft. So for you, this is really a hands-off process. Take that as being given to you similarly to the inertial matrix of the spacecraft given to you by the structural engineers, or the mass of the spacecraft given to you by structural engineers as well. So that will always be provided to you. This is not your business, okay? But your job is to use it into that equation to figure out the magnetic torque impacting the spacecraft motion. All right, enough for today. Next time, I'm going to look at the other perturbations affecting the spacecraft motion on orbit. And yeah, until then, keep up the good work, and I'll see you soon. Goodbye.